So, if you're working with industrial electricity, you know transformers are everywhere. But let's be honest, the math can feel a little intimidating, right? Especially when you're staring it down on an exam. But what if I told you it all comes down to just 2 golden rules? That's what we're going to do today. We are going to master those rules and make this whole thing simple. Let's jump in.
Okay, so you pop open an industrial control panel just like this one. Tucked away inside, there's a hidden guardian. Its whole job is to take that high, dangerous voltage and knock it down to a safe level for all the operator controls. The push buttons, the switches, the pilot lights. That little guardian is the control transformer, and its #1 job is keeping people safe.
And that really gets to the heart of the problem we're solving here. See, the big motors, the heavy machinery, they need a ton of power, often running on something like 480 volts. But you would never, ever want an operator's finger anywhere near a start button with 480 volts crackling behind it. So we've got to find a way to keep that high-power world completely separate from the low-power control world.
So how do we do it? Well, the elegant solution to this whole high-voltage problem is the transformer. It's this amazing device that bridges that voltage gap safely and super efficiently. And how it works? Well, it's not magic, but it is some really cool physics.
Let's break it down. A transformer basically has 2 main parts. You've got the primary coil, that's your high voltage input, and you've got the secondary coil, which is your low voltage output. Now here's the most important part. They do not touch. There is no direct electrical connection between them. They are only linked by a magnetic field flowing through that shared iron core.
So how is that even possible? Well, it's all thanks to a principle called electromagnetic induction. The alternating current, the AC, flowing through that primary coil creates a magnetic field that's constantly changing, constantly pulsing. That field travels through the iron core and it induces a brand new, totally separate voltage in the secondary coil. That changing part is key. It's why transformers only work with AC, and it's the secret sauce behind their biggest safety feature, total electrical isolation.
Okay, that's great. But how do we control exactly how much the voltage changes? This brings us to our very first golden rule, and I'm telling you, this is the key to almost every transformer calculation you'll ever face. It's called the turns ratio.
The turns ratio is actually super simple. It's just comparing the number of times the wire is wrapped around the primary coil to the number of wraps on the secondary. Now, in our world, the world of industrial controls, we almost always use a step-down transformer. And that just means it has fewer turns on the secondary coil, which gives us a lower voltage on the secondary side. Step-up transformers, they do the opposite, and you mainly see those used for sending power over long distances. And the beauty of this is that it all boils down to one simple, direct formula. The ratio of the voltages, primary to secondary, is exactly the same as the ratio of the wire turns. It's a perfect 1-to-1 proportion. And what that means for you is, if you know any 3 of these values, you can always solve for the 4th one.
All right, let's put this into practice. Let's say our primary side has 480 volts and 400 turns of wire. The secondary side has 100 turns. So what's our secondary voltage going to be? Well, we just set up the equation. We take the primary voltage, that's 480, and we multiply it by the turns ratio, which is 100 divided by 400. You run the numbers, and you get 120 volts, a perfect 4-to-1 step down. See? Not so bad. Now, listen up, because this is a huge tip straight from the instructors. The single most common mistake people make on exams is flipping that ratio upside down. So here's the fix. Before you even think about plugging in numbers, just take a second. Label which side is your primary and which is your secondary. That one simple habit will save you from so many easy mistakes.
So we've totally nailed how to change voltage. But what about the current? What happens to the amps? Well, this is where our second golden rule comes into play. And it's a fundamental law of physics. Power is conserved.
Now, for any test you'll take, we treat transformers as if they're 100% perfect. They don't magically create energy and they don't destroy it. What that means is the amount of power you put into the primary side has to be the exact same amount of power that comes out of the secondary side. Power in equals power out. It's that simple. And this law has a really fascinating consequence. Just look at the numbers here. If our voltage steps down by a factor of 4, going from 480 down to 120 volts, then in order to keep the total power the same, the current must step up by that exact same factor of 4. So 5 amps on the primary side becomes 20 amps on the secondary side. Voltage and current have this perfect inverse relationship.
And here is the dead simple way to remember that forever. In a step-down transformer, the voltage goes down and the current goes up. Just lock that phrase in your brain and you will never get it backwards.
Okay, so there they are, our two golden rules. The turns ratio changes the voltage, and the law of power conservation changes the current. Now, let's bring it all together and see why this stuff actually matters out on the factory floor every single day.
So really, when you get right down to it, a control transformer is doing three critical jobs for us. First, it reduces the voltage down to a safe level for people to interact with. Second, it provides isolation, creating that literal air gap between the dangerous power and the control circuit. And third, it lets us power standard devices. We can use common off-the-shelf 120-volt parts instead of having to find expensive, custom high-voltage stuff. It really is all about safety, simplicity, and saving money.
So let's wrap this up with a quick question to test what you've learned. Using our two golden rules, if you have a step-down transformer with 5 amps on its primary side and a 4-to-1 turns ratio, what's the current on the secondary side? Just think about that inverse relationship. You've got this.